Hi, I'm Alice. I'm glad that you clicked on my link. Thank you very much. And I'm going to be talking about bits and qubits. The fundamental pieces of our computers and hopefully our future. And in order to understand what a qubit is, we have to understand what a bit is in the first place. So let's start with bits. What is a bit? They're the zero and ones that makes up everything in your computer. And they're those fundamental switches like atoms in our world. Instead, bits are the untrustworthy part of the computer world since they mix up everything. And every letter you type, every picture you upload, every frame you watch, including this PowerPoint and my voice, are all made up of those zero and ones, and they form bytes, add them together, and then they form words, they form double words, quad words, strings, numbers, letters, colors, and a lot more. And how are qubits different? So qubit is the basic unit of quantum information compared to bits who store zero and ones. It stores quantum information and and it can be in an infinite amount of states. So as we see in this figure, a qubit can represent any vector that points from the center to any point on the circle. This is a unit circle, by the way, the radius 1. And as we know, a surface can contain infinitely many points. Therefore, our little vector can point to infinitely many places. Then it can represent infinite amount of states. And qubit is one of the simplest two-dimensional quantum mechanical system. And one type of qubit is an atomic nucleus. The orientation of its magnetic moment, which is its spin, can point in different direction in relation to the magnetic field, such as up or down, which act like a vector for us, according to O'Connell in their essay. And the two basic states or vectors are commonly expressed as 0 and 1, which we have in bits too, but qubits are a little more than that. It also has this complex state. It made up of a linear combination of 0 and 1, which will not simply be 0. It will be matrix that's 0, 1 and 1, 0. And it'll be a linear combination of both. And the alpha and beta is the amplitude of complex probability, which will be the coefficient that you time to the matrix that represents 0 and matrix that represent 1 in the qubit. And they're constrained by the magnitude of alpha squared plus magnitude of beta squared equals to 1, which is reasonable since we don't want to go like out of the circle, very in the circle. So according to quantum mechanics, a qubit's general state can be a coherent superposition of both of those linear combinations. And then we wonder, how do we use those qubits, right? We talk about what they are, talk a little bit how they work, but how would they help us? So here is a picture from IBM, huge company, and they're working on quantum computers, and this is one way they're utilizing qubits and larger structure made out from qubits, which is a quantum computer. And qubits, according to them, qubits can create vast multidimensional spaces in which to represent those very large problems. I'll talk about those kind of problems later, and where classical bits can, or it's very hard for them to. We need a lot more computational power for them to do this. And so this IBM used quantum computers by first setting up the space with equal superposition of all 2 to the n states, and then the problem then being coded into those into the space, and then it used the quantum algorithm and physical principles, like those two together, and we in some way magnify the amplitude of the correct answers, shrink the incorrect answers, and then maybe we repeat this process a little bit, and then we get an answer for really complex problems. And a really important concept here is entanglement. So why are those spaces helpful? Even though we understand, yeah, we can store this information, but the entanglement is coming handy when we're solving large complex problem in space. The definition of entanglement is when the particle's quantum state cannot be characteristic independently of the quantum state of the other. A pair or group of particle, in this case, are qubits, is said to be entangled. Although the parts of the state are not in a distant state, the quantum state of the system as a whole can be stated. And then we can utilize the entanglement in quantum mechanics to solve problems like this. And in our qubits, there's a particular link between those qubits, and then therefore they're entangled. And the result of measurements will reveal this entanglement. The measurement on the various qubits could result in a 0 or 1. As we see, we had probability factors will result, but still it will result in either 1. And however, the result of this measurement, individual measurements, will always be correlated with the result of other qubits measurement, and that's what made this space so useful. So what could be an example of the problem? Here, traveling salesman problem. It is a very classic computer science problem, and it's very simple. Let's say you're a traveling salesman and you're trying to figure out the shortest road to travel through cities. How many different combinations would you have to explore before you find the optimal road? Let's say if you have 3 cities, you start from city A, and then you either go to city B or B and C, or you start from A, go to C and B. It's a really simple calculation. It's very easy to figure it out, right? I can do this by hand. And then when it gets to 5 cities, there's 24 combinations. It's getting a little more complex. And then 10 city, wow, 362,880 combinations. That is a lot. We probably need some sort of computer program to help us to solve that. So yes, we understand there's different algorithms that can optimize this problem, that can solve this in less combinations. They don't necessarily have to go through all the combination to look for best road. But however, let's just say we're going to brute force this problem, because there are indeed a lot of problems that we can't find an algorithm for, and this is a very simple example that we can, but let's say what if we don't? So we can see the number grew really fast, because it goes by n-1 factorial, and like probably in like 50 or 100, it will become a really huge computational problem for any classic computer. However, let's see a comparison between classical computer and qubit computers, or quantum computers. So an example of the algorithms that IBM use is called Groover's search. It's very simple algorithm. It finds one item from a list of n items, and normally we need to check n-2 and divide by 2 elements. Well, in the worst case, but n divide by 2 in the average case in a normal computer using a normal algorithm. However, using Groover's search, you would find the item after roughly checking square root of n of the list, and then quantum computer enable us to use that kind of algorithms. And according to IBM, if you wanted to find one item in a list of 1 trillion, and each item took 1 microsecond to check, then classical computer would need roughly 1 week, while quantum computer only needs 1 second. So as we can see, we can go back to the example of traveling salesman problem. If the numbers of combinations, or the combination we need to check, goes up significantly, the computation time for classical computer goes up also exponentially. However, we can see, according to IBM, this huge difference between quantum computers computing power and classical computers computing power, and this will be very significant for us to solve other future problems. And I hope this will spur more interest and maybe more research into this field, and we can boost our technology a little more. And thank you all for listening to my talk. And if you have any question, you can email me, zxiao23@deerfield. And yeah, thank you.